Welcome to this second video about VIE for environmental research infrastructures in ENVI+, looking at the development challenges in environmental RIs. I'm Jimin Zhou, a senior researcher from University of Amsterdam. In a previous video, we introduced research support environments and discussed some example research infrastructures. In this video, we will discuss the common challenges that research infrastructures face in the environmental and earth sciences, and discuss the reusable solutions developed in ENVI+ project in particular. A successful research infrastructure is often initialized by a community whose members share similar interests in using data and software tools in a specific domain. Project-based top-down design and prototyping is then proposed, typically supported by funding agencies. And finally, the infrastructure will be made operational. In environmental and earth sciences, a large research infrastructure is often an aggregation of many small infrastructures, which are typically for communities that use data or facilities from a certain region or a country. Designing and prototyping a software stack for such infrastructure often has to tackle a number of issues like how to acquire data from distributed sources, including newly deployed sensors and local databases of earlier infrastructures, and provide a standardized way to describe the context in which those data are provided. How to check the quality of the acquired raw data using a standardized procedure. How to provide a standardized way to identify the data objects in the infrastructure so that users of the infrastructure can refer to the data objects in their publications, workflows, or other possible contexts. How to provide plans for preserving data for the long term. How to provide a flexible workflow management system which can allow users to couple software tools and services as a data processing pipeline to perform experiments or create customized data products. How to catalog the data with standardized meta information so that those data can be discovered and accessed. How to log the events during the change of the data and allow users to reproduce the evolution of the data in the infrastructure. How to optimize the usage of the underlying infrastructure and other possible issues. Looking at the entire domain of the environmental and earth sciences, there are many more infrastructures in different domains, such as ACTRIS and YAGOS are for atmosphere, EPOS for solid earth, EMSO and EUROARGO for marine, and LTER and ANAE for ecosystems. In addition, there are also some research infrastructures such as ICOS and LifeWatch that operate across multiple domains. Those infrastructures share common challenges, as we just discussed. It is therefore important to share reusable solutions to build synergy, and more importantly, to reach the interoperability among different research infrastructure necessary for cross-domain sciences by setting up agreed standards for managing data across different infrastructures. However, there are several challenges make such interoperability of solutions difficult. First, there is currently a lack of common vocabularies for different RIs to describe and share their design requirements, architectures, and management of workflows, which make the sharing of such things difficult. Second, the preparation of a research infrastructure is heavily driven by the user communities. However, those different RIs in the environmental science domains often have different development roadmaps and priorities. Third, the development of a research infrastructure is often an evolution of existing software and data assets provided by the community, which make the further software development necessarily based on the different standards and technology passes. To tackle these challenges, the first thing that is needed is to provide a common ontological framework for the research infrastructure development communities to synchronize vocabularies for describing data lifecycle and architectures. The ENVI reference model was developed in the FP7 ENVI project and was further developed in a follow-up project, ENVI+. The model abstracts the common characteristics identified in the cluster of the ENVI research infrastructure and established common vocabularies for describing data management activities and reference infrastructure patterns. To tackle the diverse views from different stakeholders of research infrastructure, ENVI reference model uses a multi-view approach based on the ISO Open Distributed Processing ODP model. In ODP, the enterprise viewpoint models the main communities that interact in a system, the roles such communities provide, and their behaviors. The information viewpoint models data objects and how they evolve as part of activities of a system. The computational viewpoints model the system components, interfaces, and the bindings between them that allow various operations to be performed. The engineering viewpoint models the system architecture and the structure, and the technology viewpoints models the technologies and the standards needed in the development and operation of the system. Using ODP, the Emory reference model models also 5 viewpoints. In the science viewpoint, based on the enterprise viewpoint of ODP, the communities of the research infrastructure are defined, such as communities of data acquisition, curation, publication, processing, and use. The information viewpoints defines the main information objects founded in the research infrastructure, such as the scientific data sets and their metadata, and describes their transition states. The computational viewpoints defines the research infrastructure components that provide computational and data services, both internally and to users. And it defines the operation that can be involved using those services. The engineering viewpoints defines how the function of a research infrastructure can be decomposed and integrated, while the technology viewpoints identifies the technologies and the standards used to implement a research infrastructure, functional components, and services. Using the ontological framework as the basis, a reference model-guided engineering approach was applied in the Emory Plus project to develop the reusable solutions to the common challenges that environmental RIs face. The reference model was used to guide not only the design of the requirements collection processes, but also the reviewing of the existing technologies and analysis of the gaps in the current RI's development roadmaps. The reference model was also used to guide the design of 6 prioritized services identified during the project, including data identification and citation, processing, infrastructure optimization, curation, cataloging, and provenance. Finally, the reference model was also used to guide the selection of the technologies and architecture design for each service. Based on the reference model and the gathered design requirements, an abstract architecture was provided for use in the development of the new research infrastructure. The development results, including the technical status of different RIs included in Emory Plus, such as the metadata standards used in RIs, and all described using the ontological representation of the reference model, and stored in a knowledge base. The objective is to help new research infrastructure to discover suitable solutions to their technical problems using the information from existing infrastructure collected in the knowledge base. The development results of Emory Plus are collected in a service portfolio available to then be tested and adopted by the research infrastructure. In this video, we discussed the common challenges in environmental research infrastructures and the needs to reuse technical solutions already developed by other infrastructure during the system development. The Emory reference model provided an effective ontological framework to describe the infrastructure lifecycle, architecture, and services. It is crucial to establish a knowledge base of environmental RIs and their services in order to facilitate the development of the reusable solutions to common challenges, not only to save on development costs, but also to improve interoperability between infrastructures. For more information of Emory reference model, please check emory.eu/rm.